Okay, thank you, Carl. Well, I'm going to present this lecture number 6 of today about the combination of apparent oxygen utilization with tracer ages, which is one of the ways to calculate respiration at longer scales, either spatial and temporal, than with algo flows. And the other one is with mass balances based on oxygen, nitrogen, phosphorus, and silicon. Okay. So first I will start.
Click on the screen.
Yeah.
And then you want to say.
I'm seeing here. Okay. Someone has to say that switch off the
blue button.
Yes. And the blue button. Switch the blue button. Okay. Well, my start is very similar to the one by Giorgio. This is the key reaction that we are interested to study, to measure, to assess. You know, we have organic matter and oxygen, and organic matter can be suspended, can be sinking, or can be dissolved. And on the other side of the equation, we have dissolved organic carbon, nitrate, phosphate, and refractory organic matter. Normally, when everyone talks about these things, always forget refractory dissolved organic matter. As I am a Vigo guy, I'm going to talk a little bit about refractory organic matter. Okay? And there are different techniques to measure, or biochemical techniques to measure respiration. We are only going to talk in this lecture about the last two, but I'm going to talk or introduce a little bit about any one of these. When you focus on sinking or suspended particular organic matter, this is the techniques that you can use. Attenuation of sinking particulate organic matter flux. This is with the sediment flux, for example. Another one is using the excess of non-lectogenic particulate barium in the particles. Another one is thorium isotope tracer method. And biochemical algo boys, which was the lecture, the previous one by Giorgio. Okay. When you focus on oxygen, then these are the three techniques, biochemical techniques that you can use. The biochemical algo boys, as we have already seen. The apparent oxygen utilization, which can be apparent or true, not real, or apparent or true, no? Combined with tracer ages to obtain apparent oxygen utilization rates along isopinal spinels or along water mass domains. We can decide where to calculate it. And also the mass balances to obtain these oxygen utilization rates or carbon remineralization, nitrogen remineralization, etc., within hydrographic boxes. And of course, models. If you focus on CO2, nitrate, or phosphate, the interesting thing of this is that if you combine this with oxygen, then you can calculate this necessary oxygen to carbon, oxygen to nitrogen, or oxygen to phosphorus ratios that are changing in the ocean, changing with depth, with the quality of the organic matter. No? And this is one of the things you see all over the day, that everyone focus or give importance to we should know which this ratio is. Well, the respiration quotient is the contrary of this, is carbon to oxygen, but it's the same idea. No? So these biochemical methods allow you to calculate in situ proper and appropriate oxygen to carbon or carbon to oxygen ratio. If you focus in the solid organic matter, you can try to do it with algo boys, not yet, but maybe. Okay, and you also can do it applying the other two methods, following the evolution of dissolved organic matter along an isopycnal surface, and if you have the age at the same time, or also doing mass balances. In fact, I will show you an example on how to use dissolved organic matter in combination with tracer ages to calculate the mineralization rate of dissolved organic matter in the ocean. So in this lecture, as I told at the beginning, we will focus on oxygen utilization rates or in mass balances, okay? Only these two. Estimation of apparent oxygen utilization rates from apparent oxygen utilization to oxygen utilization combined with tracer ages. It is winter, we are in a temperate or subpolar area, then the water becomes to be colder, and we have a winter mix layer, then this water mass is denser, sinks, and start to flow in the ocean. No? This is what this represents. And so we are going to focus on this piece of water, this water which is in between density sigma 1 and sigma 2. For example, between 26.1 and 26.3 density. Okay, so in a narrow range of densities, and we are going to study what is the matter when this process takes place. During winter, when the winter mix layer is forming, the air and this winter mix layer are in equilibrium or close to equilibrium. Maybe yes, maybe not. This is why we have to differentiate between apparent oxygen utilization and true oxygen utilization. Okay, but let us think in the beginning that oxygen and also these tracer ages, the CFCs and SF6, which are the most commonly used nowadays, are in equilibrium with the atmosphere at the time when this water mass was last in contact with the atmosphere, and then start to separate from the surface, so no more contact with the surface ocean, and start to travel to lower latitudes. So, dissolved oxygen, no problem with this. We have seen this today several times. Dissolved oxygen saturation, we also have talked about that. It is just the oxygen of equilibrium with the atmosphere at a given temperature and salinity. And in fact, we can calculate it directly with this equation, which is a combination of temperature and salinity. So with salinity and temperature to calculate the oxygen saturation, and this is the oxygen in equilibrium with the atmosphere. Preforming dissolved oxygen. The oxygen that you really measure at the time when the water mass is formed, because it could be oxygen saturation, or it could be not. If the winter mix layer is very deep, for example, at very high latitudes where the winter mix layer can have more than 1,000 meters, even 2,000 meters, it is not possible to equilibrate with the atmosphere. And then really the initial of preforming dissolved oxygen is below the saturation level. So if you use apparent oxygen utilization to calculate age, you are overestimating the age, because the true oxygen concentration is below if you are in this kind of areas. But it could be also the contrary, that at the time that when the water mass is formed, you can have more oxygen than the oxygen of saturation. So apparent oxygen utilization is oxygen saturation minus oxygen concentration. And true oxygen utilization is initial oxygen minus oxygen. So we always use apparent oxygen utilization, and it is normally okay, but we should have in mind that we should use real or true oxygen utilization. But the differences could be more or less higher, no? And there is ways to avoid having this problem, as we will see. How we measure the tracer ages was following CFC11, CFC12, SFC6, which are all these gases here that are in equilibrium with the atmosphere at the time of water mass formation. And you also can calculate the saturation with an equation similar to the one for oxygen, which is the one here. And then you can estimate from the concentration that you find in the water column and this trace gas saturation, what is the partial pressure of equilibrium with the atmosphere at the time when this water mass was formed. So these are the atmospheric time studies of these gases. CFC12, CFC11, SF6. Okay, they were at very low concentrations in the 40s, started to increase the concentration in the 60s, but with some differences between them. And of course, for example, for CFC11 reached their maximum in 1990, but SF6 is still growing. So you can use these gases to estimate the age of the water when they are in the linear part. Because if you take this here, you don't know if the age is this one or is that one. Okay, so you have to use the linear part of the history of the gas. And you can also divide one gas by another to find new ratios. But the idea is you measure, for example, here, the concentration of any of these gases, which is not an easy matter, I have to say, because it is difficult to collect them. You have to take care or no bubbles, no contamination on board. You should normally measure on board, but you can also measure in the lab. But it is a gas chromatography combined with cold traps is a really difficult method to measure. We can talk about then if you want during the practicals. I have no time to explain this here. But the issue is that when you know the concentration of any of these gases here, you calculate from this concentration using the saturation, what is the partial pressure at the time that this gas was last contacted the atmosphere, and then you see, oh, is this one? So the last time that this water was in contact with the atmosphere was in 1980. We are in 1995, so it is 15 years old. Okay, this is the way to calculate the trace of age.
Because they don't interact with anything else.
Yeah, well, they are inert. Well, almost inert, not 100% inert, but for our purpose, they are inert. Yes, and oxygen obviously is not inert. So you have, and the other thing is these gases, because of the anthropogenic action, were concentrated in the atmosphere. It has a story that we can follow, and we can know 500 was in the year 1990, no? And these things that allows you to calculate an age based on the atmospheric histories. No? You have to measure oxygen, you have to measure CFCs or FFCs, these trace of ages, and with these two things, you have how much oxygen was consumed and how old is the water mass. So we have all we need to calculate oxygen utilization rates. So we can do it in a very simple way. The only with 2 points, say the initial point, which is not a point, because if you assume that age is 0 and oxygen saturation, then you only need 1 point, that one. You take a sample here, measure the oxygen, calculate the AOU, measure the trace gas, calculate the age, and do this. Apparent oxygen utilization divided by trace age. Of course, if you have another sample here, another one here, another one here, you can calculate the apparent oxygen utilization rate in any of these places. But this is where we have a problem, because you are assuming that oxygen is in equilibrium with the atmosphere at the time of formation. So we are assuming that apparent oxygen utilization here is zero, but maybe it is not zero. So if we are using this method, we should calculate the true oxygen utilization rate. This means not the oxygen saturation, but the oxygen measured at the time of water mass formation. So you have there to measure, or use the World Atlas years of data to calculate the saturation state of this water mass at the time when it is formed. No, it is, you can do it, but you know, it's an uncertainty really. So yeah.
How big are the differences between the two and apparent?
If the water mass is deep, is if the winter mix layer is very deep, it could be 60% difference. Okay, so if you are working with deep water masses, you have a problem. If you are working with mesopelagic, which is our case, it's not so big. You know, it could be 10%, 15%. But anyway, you will see now that this is not so bad. Okay, so it is better to go for this other situation. You have not only one point, you have several points following the water mass. Of course, as I told before, you can calculate this one, compare with that one, this one compared with that one, etc., and you obtain several of them. But you can also do this. Represent the apparent age against the apparent oxygen utilization. Okay? And what you normally obtain is a straight line like this. So really, you can take this slope, the slope of the linear relationship, as the oxygen utilization rate. Of course, it's not an oxygen utilization rate over individual point, but an oxygen utilization rate that considers the latitude where you start and the latitude where you finish. For example, I want to see what is the oxygen utilization rate in the subtropical North Atlantic. I take the points that are within that range of latitude and calculate like this. So this is an oxygen utilization rate, which is an average for a big area, no, for thousands of kilometers. And also an average that considers decades, not only 1 year, as in the case of the algal floats. Here we're talking about decades, if you do it like this. And so in this case, the origin intercept is the difference between the true and the true and the saturation oxygen and oxygen saturation. So you can use this intercept to calculate or to see what is the difference between oxygen saturation and true oxygen at the time of formation. Okay? This is what I said before, that we can avoid the issue of using true oxygen utilization or using apparent oxygen utilization. Because if you are interested in, I want to know what is the matter in this area, in this square. So I study the water that comes in and comes out and look at how the apparent oxygen utilization changes in this time, which used to be 1, 2, 3, 4 decades, whatever. I will show you examples of that. Maybe someone is surprised because this is a straight line. Because if it is a straight line, means that there is no limitation by the substrate, by the organic matter. So this means that if you have this line, the amount of organic matter that is feeding our two isopycnals has to be the same all over the root. So when you get this, this means that you are in an area, for example, as the subtropical ocean, where probably you have a very stable situation with a flux that is in any place of the subtropical, except if you are in the boundaries, is going to be a constant flux. So there you have a constant supply of organic matter, and then you have this straight line. But of course, you can also have this. Okay? And when order the decay of oxygen as we are talking about apparent oxygen utilization is one order, not decay, contrary to decay, no? But this is, or represent better this situation. You have close to the formation area at higher latitudes, more important entry of organic matter. And then when you go into the subtropical, for example, then the flow decreases. And as the oxygen consumption is affected by the amount of organic matter that arrives to this level, then you are going to have something like this. But again, if you are interested in working only in this area, it's like taking this, and this is a straight line. So, and when you work with dissolved organic carbon, in this case, so look into the reagents, no? What you obtain is this. Why? Because the main entry of dissolved organic carbon is by the time of formation, really. There is not a vertical flux only in some places and in some given situations, but normally the big entry of dissolved organic matter is when the water mass is forming. And this is the kind of result that you obtain, a one order decay. And as you can see, you can do it not only with oxygen, as before, if you have DOC measurements, you can also produce this kind of graph and obtain the decay constant of one order decay constant of oxygen, sorry, of dissolved organic carbon utilization. I suppose that you notice that this is like a wonderful word. No mixing. This got a mass, just form here, move around, and don't mix with anyone. So you can calculate this without any consideration about mixing, about advection, and all these things. No, life is not like that. The true ocean, or the real ocean, what is true is that if you want to calculate the age at this point, what we are showing now, what we have shown now, is formation and arrival there. But the real thing is that this point can also be, or the water that you have here can also come from here, from there, from other places. So there is mixing in the ocean. Even more, you can depart from the same place through different routes to arrive there, no? So it's more complex than simply water mass formation, sinking, and displacement without mixing with anyone. So we have to take into account mixing. If we do not have into account mixing, then all these calculations can be helpful, but are not true, no? Or are a very long way is necessary to arrive to a true number, no? So what is the way to solve this? Well, the most sophisticated one is using the transient time distribution, which is based on this, where it says that age is not, each water mass has not an individual age. It has a distribution of age like this, with a more probable age, and then also probability to have different ages for the same one. Okay, this is a statistical method based on the water mass analysis, which is really complex, I think, out of the scope of this course. And what I'm going to propose you to show you is a method to correct the water mass mixing in a less sophisticated, in a more simpler way, but effective anyway. Okay, which is well, normally this water mass is water mass 1. When it moves along the ocean, it's going to mix with the water above and the water below. Okay, water mass 2 and water mass 3. So it is the problem of mixing of 3 water masses, the one that you are interested in and the other 2. This can be solved with salinity and temperature with a very simple equation. The salinity of your sample is a combination of the salinity at the time and place of formation of water mass 1, water mass 2, and water mass 3. The same for temperature, and then the continuity equation. So with salinity and temperature, you can obtain the proportion of each one of these 3 water masses at this point, at any other point. in the practical, we will do that. So if you have any doubt, we can talk about that. But the idea is that normally the water mass mix with the one below and above, and then you can solve the mixing just solving this very simple system of 3 equations with 3 unknowns. And when you do that, you can do a multiple linear correlation of the apparent total utilization with the water mass proportion, and the residuals of this correlation is delta apparent oxygen utilization, which is the apparent oxygen utilization independent of mixing. These residuals do not depend on mixing because you have done the correlation, and then the residuals does not depend on mixing. The same for the age. You make a multiple linear correlation of age with water mass mixing, and you obtain delta H, which is not dependent on mixing. So then you can take your delta apparent oxygen utilization, correlate it with your delta H, and the slope of this correlation is the apparent oxygen utilization independent of water mass mixing. I said this is not perfect, but it's much better than do nothing. But the next step is transient, the TTD, the transient time distribution. Okay, this could look complex, but it's simple because it's equivalent to make a multiple correlation with salinity, temperature, and to correlate apparent oxygen utilization with salinity and temperature, and use the residuals. The same with age, salinity and temperature, and then you use the residuals. So it is just doing a couple of multiple linear correlations to eliminate the effect of mixing and use these residuals to calculate the apparent oxygen utilization not affected by mixing. Why I say that? Because if you have this water mass, which is water mass, obviously, which is young and with high low apparent oxygen utilization levels. And if you mix this with this water mass, which is old and with high apparent oxygen utilization levels, most of the variability that you have is due to mixing one water with the other. And what you really want to know is take that off and fix on the variability associated to the material that is respired in the water mass that you are studying, not because you are mixing one with which is older with a lower amount of organic matter, with the other which is younger with a high amount of organic matter. One of the examples of the exercise that we will solve tomorrow will let you know how important it is to do that correction.
I wanted to ask you.
Yes.
The same thing.
Yes. How important is it? You can apply those onto the Argo boards. These things. And well, and another way of doing it much faster is just making a direct correlation of apparent oxygen utilization with salinity, with temperature and age directly. And the coefficient of age is the apparent oxygen utilization independent of water mass mix. And now I'm going to show you an example, as I told you about DOM, no? Because I'm a DOM guy. This is a distribution from the very north, from Iceland to the Antarctic circumpolar current. We did a water mass analysis more sophisticated than just with salinity and temperature to define the main water masses in the deep ocean. And we are going to concentrate on upper North Atlantic deep water now, which from their formation area to almost Antarctica. Okay? What is the matter with DOC along that water mass? And what we did is just what we show you. So you can publish papers doing this simple approach. No problem. And this is the recent one, 2019. Okay. We do the correlation with the water mass analysis to obtain the delta DOC, and the same for the age. Okay. And this is what we get. This is from almost 70 north, crossing all the Atlantic into the South Atlantic. Okay. is following this route. And H do this. Okay. Well, this is delta H and delta DOC. Don't worry about having positive or negative numbers. It's a residual. If you don't like positive and negative, add something to here. All of them are positive.
Easy.
Yeah, I have a fight with a reviewer because of that. DOC cannot be negative. These are when you represent one against the other. You know, you represent DOC again. The points are. You see how the points are. You know, you see a decline and then an increase. So at the beginning, when the material is fresh, you have a clear decline. But when you arrive to the equator, you do not follow a straight line. You have an increase. You really have this. You have this part. You need an equation that has a positive term here to reproduce this increase. Okay, so you have a decrease with this annual rate and an increase with this rate. I would expect to have something like that, but really you have this. Why? Because this is refractory, this of the organic matter. So what you see at the beginning, you always have refractory organic matter formation. But at the beginning, the dominant issue that you be in the DOC distribution is the decline of the bioavailable dissolved organic matter. But when the bioavailable dissolved organic matter is finished, what you see is the increase of the refractory. Because you have no dissolved organic matter there, but you have a flux of particles all the time. And this refractory organic matter is a result of the oxidation, the mineralization of that particles. No? So this is the kind of information that you can obtain doing these approaches. And well, the other thing that I'm going to introduce is the calculation with mass balances. Okay, and everything starts defining a box. I say, well, defining a box, first you have to have a scientific question to decide where you want to go there, no? And for example, we decided many years ago that we would like to see how the dissolved organic carbon that flows out the Mediterranean Sea affects the consumption of oxygen in this area. So we did this hydrographic box. And here, our question was, what is the matter in an area so dynamic like this one, where you have the Canary current, the Mauritanian current, the Cape Verde front, an area very dynamic and active. Okay, so you have to have a question and then decide, I want to do this box, and the next point is doing a cruise to do the box and obtain the data that you need. And once you have this, when you have the box, the hydrographic box, you also will solve a problem about the hydrographic box in the practicals, okay? And here the idea is just first calculate the mass transport. How much water is entering, how many square groups are coming here, and going out there. In each layer, at least the surface layer and the mesopelagic layer, which is the one in which we are interested now. Okay, so the first is calculating the mass transport. The normal way of doing this is making an optimized geostrophic plus Ekman constraint calculation. I don't know if you have knowledge about the way of calculating geostrophic flows, but well, we have the practical to do it. But the idea is the following: if you decide, or you, for example, that 2,000 meters is a reference level where there is no movement, no displacement, and at this level, then if at this point the water column has a density of 1.27, okay, and in this point it is 1.24. If there is no any movement between here and here, this column has to be higher than this one. If this is higher than this one, the water has to move from here to here. But because of the rotation of the Earth, then the flow is really in that direction. And this is the contrary. In that case, it's going in. So it is just based on the different dynamic age in the ocean. Okay? You do this first, and obviously, when you close the box, the mass balance should be 0, and the heat balance should be 0. And if it is not 0, it is because the level that you choose as no movement is not right, and you have to play with it to be able to have a 0 balance of salt and temperature. Okay, well, we will see this in the practical. Okay, but the idea is that you need to know the currents some way coming in this case, coming in, and coming out. Okay. Once you know this, you multiply these currents by the concentration of the variables that you want to make the budget. For example, oxygen, carbon, nitrogen, whatever you want, and then make a net budget of how much carbon is going in, how much is going out, how much oxygen is going in, how much oxygen is going out. And this difference is just the how to say, the net one, the net ecosystem, the net apparent ecosystem production. Okay. So, for example, in one of these cases, normally we divide the water column in several boxes: surface, central, intermediate, and deep. And what we do is just a balance, considering the fluxes that is going in. This one is lateral flux from this side, lateral from the other side, outgoing, and then the vertical fluxes as well. Okay, it's just making a balance of what is entering the box and what is going out of the box. Okay? And also, of course, the equilibrium, the exchange with the atmosphere. You can calculate, or one of the most interesting things that you can calculate is this one, the time that the water is into each of these boxes, because it gives you the time scale that you are considering in your oxygen utilization rate calculations. And the way to calculate the time is just taking the volume and divided by all the entries or all the output. Okay? And this is a variable that is really interesting to consider. The same for the mesopelagic, which is the one that we are working now. Sorry, this one. These were the fluxes, just the transports, and then to obtain the budget, you have just to multiply the volumes by the concentration of the variable that you are studying. Okay, and the same for the mesopelagic. Here are only the volumes, and then you multiply the volumes by the concentrations, and you get your net ecosystem production. And the example is this one. Okay, in the state of Gibraltar, you have a very the Mediterranean water is very salty and dense. Then when it enters in contact with the Atlantic water, it sinks from the sill here to about 1,000 meters. The amount of Mediterranean water which is crossing the Strait of Gibraltar is about 0.4 spectrums, but it mixes with the central waters of the Atlantic here, and the final volume out of the Gulf of California is about 2.7 spectrums. So there is, this water mass is sinking, but it's not because of the formation of in an area that is very cold. It's not the formation area at high latitudes. It is just because of the difference of density between the Mediterranean and the Atlantic. When the Mediterranean water gets in contact with the Atlantic, it sinks to 1,000 meters. And in that sinking, there's an entrainment of all the central waters that are here. So most of the volume that you find at 1,000 meters comes from here. And the water here has high concentrations of the soft organic carbons. So you are injecting a large amount of the soft organic carbon at 1,000 meters. through a mechanism that is not deep winter mixing. Okay. And well, this is the distributions that we get, and these are the balances that we obtain. This is just an example of all that letters that you see in the box in and out. And well, the result, the final result is that DOC accounted for up to 53% of the respiration of carbon in this area. And this is created by this Mediterranean water that in the state of Gibraltar. And this is just another example to show how you can use the boxes, the box models. If you have data of DOC, oxygen, carbon, whatever, and can calculate these fluxes. And once you have the fluxes, you multiply that by the concentrations and look at the result. And you can obtain this kind of interesting results because, well, this is one of the few areas where you can find a phenomenon like this, that DOC represents more than 50% of the oxygen respiration. This is maybe one of the very few places where you can find something like that. Okay, and well, to finish, just a brief summary of what we have been talking in this time. Well, the upper subsistence rate estimates are compatible with large space, hundreds to thousands of kilometers, and time. This is from say, well, 1 year if the box is small, 1 year to 100 years or so. So these are scales that are close to global biochemical models. I think could be more comparable with the results from global biochemical models or these more than microbial estimates, not ecological. Combination of tracer ages with water mass analysis produce reliable results, allow calculation of these apparent ionization rates, allow to quantify the stoichiometry of organic matter degradation. I didn't show any example of that, but you can do it. And allow to quantify the temperature dependence of apparent oxygen utilization. This is another point that I have not introduced, but could show you examples of that. And allow to study the contribution of the OM to respiration of the ocean, as we will see in a couple of examples that I showed. And of course, it's large uncertainties around. And it is, I would say, it is precise but not accurate. No? So I think that the order of scale is okay, but maybe you have a plus minus very large because you have a lot of assumptions and a lot of things to measure that has their own error. And finally, you have a large or relatively large error when you do this kind of calculations. But at least I think that they are precise. Okay. And that's all. Thank you.